A quantum hardware startup overcomes atom loss, dramatically extending usable computation time and enabling self-repair in quantum processors. Among quantum approaches, the neutral atom method has surged in prominence, using tightly focused laser beams to trap single atoms as qubits in vacuum. Unlike superconducting routes led by Google and IBM, neutral atoms scale naturally from hundreds to thousands of qubits with optical control. The key advantage is that atoms are standard natural particles, easily scaled by light without artificial fabrication. Yet the system is vulnerable. Residual gas molecules periodically collide with trapped atoms, causing them to escape the tweezer. Laser heating during gate operations or readout can also cause atom loss, interrupting calculations and forcing a restart. When a single atom is lost, the entire quantum register is disrupted, ending the current computation. This interruption, stop, reset, and restart, limits continuous operation and thwarts long, complex algorithms. Atom computing has recently broken through with an atom real-time recovery system that enables self-repair without halting the machine. In December, the team published in Physical Review X detailing a closed-loop system that monitors, replenishes, and reuses ancilla atoms mid-operation. The core idea is a dynamic logistics and maintenance system housed inside the quantum chip, turning loss into a replenishment opportunity. Outer biome atoms serve as natural qubits, with two stable ground states and a large separation between cooling and qubit transition frequencies. This physical property lets researchers manipulate select atoms without disturbing neighboring qubits, enabling precise control. From this, atom computing built a closed-loop control system for continuous monitoring, recycling, and supply of atoms. First, real-time global monitoring scans the tweezer array during computation breaks to identify which atoms have fallen behind or which ancilla qubits are idle. Next, a magnetic optical trap about 300 nanometers below the main array stores a reserve pool of cold atoms. When a vacancy appears, a tweezer arm captures a new atom from the reservoir and moves it precisely into place. Meanwhile, auxiliary atoms that have been measured and decohered are cooled and reinitialized for reuse. The challenge is keeping qubits invisible to avoid crosstalk during cleaning and moving operations. Meticulous optical routing and timing ensure that running data qubits remain undisturbed during ancilla maintenance. Matt Norsha notes that maintaining a stable atom count is essential for multi-layer logic gates and practical quantum computing. Beyond extending runtime, the technology addresses the core cost of fault-tolerant quantum computing by recycling ancilla qubits. In demonstrations, mid-circuit measurements detect errors and replenish atoms without interrupting the computation. This capability is crucial for error-correcting codes like surface codes and color codes used in scalable quantum architectures. Atom computing's progress isn't just lab glory, it signals steps toward practical, fault-tolerant quantum machines. By 2024, the company already crossed 1,000 physical qubits with strong coherence, and real-time recovery adds critical reliability. DARPA selected atom computing for the Quantum Benchmarking Initiative at Stage B, validating industry impact and roadmap commitments. Microsoft has collaborated on error-correcting protocols, demonstrating 24 entangled logical qubits and 28 physical qubits with error detection and correction. The goal is a metaphorical, perpetual motion of computation, self-sustaining, endlessly running quantum machines in the long term. Real-world challenges remain, from faster atom transport to lower control delays and the growing wire and signal processing complexity. Nevertheless, the atom real-time recovery approach marks a pivotal shift toward longer, fault-tolerant quantum computations. The path from the lab to large-scale deployment remains challenging, but the potential to keep quantum systems running longer is clear. If the pace continues, quantum computers could begin to address practical problems with near-continuous operation in the coming years. The 3-minute journey through this breakthrough reveals a future where error correction is cheaper, and computing time becomes nearly limitless. Background music swells as we glimpse the quiet, high-precision world of neutral atom quantum hardware. Scene transitions will continue to reveal the science behind the breakthrough scene by scene. This is a story of resilience and engineering that turns fragile quantum bits into a durable, scalable resource. From the lab bench to the frontier of fault-tolerant computing, the journey continues. And the story is still being written as researchers push the boundaries of what is possible with neutral atoms. The video concludes with a nod to the future where quantum machines operate with minimal interruptions and maximal uptime. End title: The Atom Recycling Quantum Computer. Self-healing, scalable, and ready for the next leap in computation.